So my name is Enrique del Rey Castillo. I am a lecturer here at the University of Auckland. I am also part of ASG, so I am putting myself a medal, patting myself in the back. Feels a little bit weird to be both member of the organization and the presenter. But anyway, my friends asked me to present on this topic, and here I am. Most of my teaching and research is purely structural, mostly on seismic behavior and seismic strengthening of existing buildings. But a couple of years ago, maybe a bit more, 3 or 4 years ago, I started thinking about why we have buildings in New Zealand that suffer damage and sometimes collapse. And that's what I'm going to talk about today. So it's not a purely structural problem, it's more construction management or cost estimation problem. Now, like I said, I started this a while ago, and it's going to last for another couple of years. So I'm going to talk only about why I'm doing this, the different tools that I'm using, why I'm doing it this way, and a little bit of initial results. I want to give a big shout out to the students. They are the engine of this project, and without them, this would not be possible. They are there, so you can give them a huge clap. And you can see that they are funding the project. Right, so why? This graph is from the 90s. And back then, from California, not from New Zealand. And back then, it was kind of innovative to say that buildings shouldn't collapse in earthquakes. In the 70s, 80s, even in the 90s, buildings were collapsing and people were dying, even in developed first world countries. So saying that no building should collapse ever was kind of revolutionary. But now, fast forward 15, 20 years, this was developed after the Canterbury earthquakes by the Royal Commission, based on societal expectations. And society not only want to survive an earthquake, but they want to don't lose their building or not have to unoccupy the building, their homes, or their offices for a long period of time. Now, there are different ways of achieving that. One is to use low damage devices, dampers, base oscillators, you name it. There are many of them. Proprietary, expensive, difficult, easy to design. In my opinion, they will not be widely adopted. If you are designing a hospital, fire station, yes, perfect. It's the perfect application. But not for every building, every office, every residential building. I think, in my opinion, we should have strong, stiff buildings that don't suffer damage. How do we do that? We can reduce the drift, 5%, 1%, even less. We can reduce the ductility, 1, 1.5, 2. Basically, we're reducing the damage. So it is a low damage design approach. We just don't use fancy tools that make other people rich. Now, when I started talking with friends, engineers, colleagues about why we don't design strong and stiff buildings like they do in other countries, like Japan and Chile, a lot of people smarter than me, with much more experience than me, told me that it would be too expensive. But a lot of other people, also smarter than me and also with more experience than me, told me that that's actually a perception. But both of those two groups of people didn't have the data. It was their opinion. So that's what I intend to do, to understand what are the construction costs of designing more seismic resilient buildings. Seismic buildings designed to a higher seismic demand. Now, I started this project looking at, my initial approach was, let's take a few buildings, 5, 10, 15, that have already been designed. We know the cost, we know the seismic performance, and then redesign them to a higher seismic performance or reduce ductility or reduce drift, and see how much more it will cost. But that was very, very difficult. People didn't want to share their designs, owners didn't want to share how much they paid for their buildings, and for some reason that I don't understand yet, in New Zealand we don't design buildings, every building is different, with weird corners, with re-entrance. I know architects, my wife is an architect, but we should try to design regular buildings, not concrete walls here, steel braces there. No, just design buildings that are regular and the same in both directions. Anyway, the point is that if I take a building that has concrete frames there and concrete walls there, I can only apply what I learned from that building to other buildings that are like that. So it was quite limited. So I sat down, I thought, okay, I need to rethink how I'm going to do this. And I decided to develop an extensive database of buildings. And by extensive, I don't mean 200, I mean thousands, 10, 20, 30,000 buildings with different structural systems, different foundation systems, and hopefully different non-structural design. Now, I can apply that to a large spectrum of buildings, because if I have buildings with reinforced concrete frames here, and reinforced concrete walls here and here, I can use concrete frames here and concrete walls there, if that's what the architect or the engineer wants. Now, by having such a large database, I can use machine learning as a predictive tool. The main premise of machine learning is to have large databases. 500 data points is not enough. And I can use that to identify cost drivers. What is driving the cost, other than the size of the building, of course. Now, because designing 10,000 buildings is not feasible, what I'm doing is I'm using parametric design with Revit, with Dynamo, with different tools to parameterize the design. I will talk about that in more detail later. And I'm using late-stage estimation techniques. Again, I will talk about that in a second. And hopefully, I'm trying to recruit a student to do a detailed structural analysis. So it's basically a data set of 3 sets of data. Buildings, each building being different, the associated cost, and the associated seismic capacity or seismic performance. Now, this is the whole program, 4 years. So we started with a literature review, trying to learn cost estimation methods, construction management, what is all of this about. I never learned anything like that in university, so it was kind of out of my comfort zone. And then developing the methodology, how are we going to create 20,000 buildings? And we are now starting to get data on frames, walls, and steel buildings, and hopefully next year expand that to foundations and related earthworks and non-structural elements, put everything together, and create a tool that we can use, relatively simple, and give us an accurate cost, construction cost for the project. Now, we started with the literature review. I'm not going to bother you with a lot of information. The main thing that we learned is that the early cost estimation methods at the early stages of the development process are not very accurate. So I'm going to develop a building, so many square meters, how much per square meter, that's my cost. That the best accuracy we can get is plus minus 25%, but it's more frequently minus 50, half, or plus 100, twice as much. But as we move forward in the development, in the construction process, the estimates are more accurate. At least plus minus 5%, but usually more like 2, 3%. So we want to use final stage cost estimation methods in the early stages of the building development or design. Now, the second thing that my student did is read something like 120 papers from all over the world on the use of predictive analytics to estimate construction costs or building costs. He collected something like 70-something cost drivers or parameters that affect the cost, and then he ranked them, and then he scored them. So we know not only which one is more important, but by how much. So if we look at the first 5, we can see that the score is significantly higher than all of the others. Now, this is useful to make decisions with the developer, with the client, with the architect. Some of these are sensible, expected, like floor area, a number of floors. Of course, if your building is big, it's going to be expensive. But some others are not so much, like number of elevators. In hindsight, it makes sense. If you have 4 elevators, it's not going to be 4 times more expensive than 1, but it's more expensive. The problem with this is not data in New Zealand, so they will not have seismic provisions. So we need to redo it again, basically. Another thing that we learn is that the predictive tool doesn't really matter. Computer scientists get all over very excited about developing new machine learning algorithms. It doesn't matter. What matters is the data, that you have a lot of data points representative of what you want to predict. Now we move on to the very limited research with New Zealand data. This is a PhD thesis. And what this person did is investigate the building development cost. So it's not only design or construction, it's everything involved in development. Hiring people, procurement, everything. Now, there is a lot of information in here. I find this graph a little bit confusing. It took me a while to understand it. But basically, what I want you to focus is each of these segments is one of the categories of factors that affect the construction cost. Now, the closer to the center, the more influence they have on the final cost, development cost, not construction cost. And we can see that as our industry at the top is the closest one to the center. So design cost, construction cost, procurement cost are the most or have the highest influence on the building development cost. I think that's good because we have a little bit of leeway on how we design buildings, and we can, up to a certain point, control that. Now, this slide, on the left-hand side, we have the information from the quantity surveyors. On the right-hand side is a final year research project from Canterbury, from Professor Rajesh Dakal. Basically, what this is telling us is between 20 and 25, 30% of the construction cost, this is construction cost, comes from the structure. So structural costs, 25% of the total construction costs. So even in the worst case scenario, that making buildings suffer less damage or no damage costs 30% more of the structural cost, is 30% of 25%. And then our buildings don't have to be unoccupied for months, years. The businesses can continue making money. The people don't lose their homes. I think it's worth it, even in that worst case scenario. Right, now we move on to how we are developing this database. We start with Resist, which is a software from NZ SCE that does preliminary seismic design. Now it has several limitations, some quite critical. Most of them can be overcome, but it's extremely fast. Like I can literally design, preliminary design, a building in 1.5 minutes. It's super fast. And it's very easy to change between different structural systems, change different structural sizes. So it's very powerful in that sense. Now we start with the size of the building in floor and in height. We start by selecting dead load, live load, what type of floor we have, what type of internal wall we have. Then we move on to where our structural system is. We can have concrete walls, concrete frames, brace frames, and another one, I don't remember now. We select where they are, where the walls, in this case walls, are going to be. We can see it on that graph on the right-hand side. Then we select the seismic hazard factor. I have one hazard factor of 1 there. I know 1 is not in the current code, but that's the maximum that Resist admits. The type of soil, and then we change the structure. We change, in this case, is frames. We change the diameter or the breadth and the width of the columns. We can change the number of bays, the number of frames, until we hit 100%. If we are over 100%, it doesn't comply. Below 100%, it complies. From here, we can get a lot of information, but I'm not going to go into too much detail. We can get displacements, we can get drifts, we can get engineering reports with all the loads, base shear, we can get architectural reports. I'm not selling the software, I'm just saying that it's quite powerful, even though I'm just brushing over it. From here, we get the dimensions, the characteristics of the structure, which we use in Revit to model the building. Now, because we don't want to model too many buildings, we use a tool called Dynamo, which is an add-on that allows us to parameterize the design. So we can change the beam in this case. We can change the floor slab, different type of floors, very quickly. It's a visual parametric modeling tool. And then Revit creates the model automatically. With one click, gives us the quantity takeoff. Then we go to QV Cost Builder, which is the tool that quantity surveyors use for costing. And we multiply basically, for example, square meters of floor times the cost of the floor. And we can parameterize further this relatively limited number of beam models by changing, for example, the thickness of the topping, changing from Comfort 60, Comfort 80, different types of steel. For example, for a fixed reinforcement ratio, it's not the same to have a lot of small bars than fewer bigger bars from a costing perspective. It has different cost. Then different cities. So all of that is implemented into the database by MATLAB or Python or Excel. Now I'm going to give a very brief overview of the results that we have so far. So this is concrete frames. We can see that these are the models developed in BIM only. So we have 3 and 8 stories, 3 and 10 grids, 2 hazard factors, 0.4 and 0.7, and 3 types of concrete floors. These are together because it's the same, well, it's not, but we consider it as the same dead weight. So this gives us 16 BIM models. But then, by using different costs in different cities, different reinforcement ratio, different concrete strength, blah, 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 we get, I think, about 1,300 models, only for concrete frames with one type of foundation. So when we incorporate different types of foundations, non-structural elements, it compounds, right? Now, these are some preliminary results. They are not final. They can change. They can be wrong. They are not final. But I think it gives a good gist of what we are getting and what we will get. So we can see that the cost in Auckland is, I would say, significantly higher than in Wellington, in Christchurch, for all buildings. Obviously, the bigger the building, the bigger the difference. In Wellington, it's about 11% cheaper than Auckland. Christchurch, around 9% cheaper than Auckland. This one is interesting. I like this one a lot because I know, by the way, before I continue, I know that hazard factor of 0.4 in Auckland is not realistic. Even if we are changing the seismic hazard model, it will not increase to 0.4. But we are just looking at all different possibilities. And that can be used as a proxy for reduce damage, like we want the building to remain elastic. Anyway, I was saying that I like this slide a lot because it shows that the in-situ floors are more expensive, the most expensive. And then between composite and precast, composite is actually cheaper than precast. So in theory, we use precast because it's cheaper. But if it's not cheaper, it's actually more expensive, even at the same cost. And it doesn't work from a structural point of view, or it's so difficult to make it work, then maybe we should stop using precast and use only composite floors. Anyway, I think we should stop using precast, period. I don't like precast floors. Another thing is slenderness ratio. The cost is higher for slender buildings. So that building in 4th Street, which is like this thick, but it's extremely tall, is more expensive than if you build the same building with the same floor, but it's more squat. So I think those kind of rule of thumbs are important. Now, this one is very good, I think. We have 3, 5, and 10 stories, different column sizes, which represent different seismic capacities. The difference is so tiny that we cannot even see it. The largest difference for the largest building, 10 stories, is 2.4% to increase the hazard factor from 0.13 to 0.5. So increasing the hazard factor from 0.13 to 0.5 is 2.4% more expensive. Again, this doesn't include foundations, earthworks, which is a big cost, I think, is going to be a big cost, or facades or non-structural elements, but everything else being equal, we are only increasing the cost to 0.4%. Even if it's 5%, isn't it worth it to increase the cost 5%, assuming that the hazard factor goes from 0.13 to 0.5? Now, we started with frames. Now I'm going to talk a little bit about concrete walls and then steel structures. For concrete walls, we are looking at same building size, height, size of the structure, reinforcement ratio. Now, I would like to look at different wall layouts, but this is very difficult to do, both structural and costing, because what is the difference in cost between this and this, assuming that the amount of concrete is the same? It's very difficult to measure that. And what is the seismic performance between this and that? You need to do a very detailed analysis. But I think it would be interesting to say to the architect, I know you want the walls there, but it's going to be 10 times more expensive or 10% more expensive. But I don't know if we can do that. The second thing that I would like to look is how much more expensive, if it's more expensive, between that one and that one. We know that from structural point of view, we can do that one with overlapping squares of stirrups, or we can do this one with individual ties. And structurally, it's the same. I mean, that's what the code says. Now, which one is more expensive? If we knew that, maybe we will always do that, or we will always do that. One challenge we have with walls is as the building gets bigger, both in size and height, and the hazard factor gets higher, we need more walls. So in this case, we have 6 walls. The building is 50 by 50 and 8 stories high, and we have 6 walls in each direction. The walls are, I think, about 12 meters long and 300 or 350 thick. It's a lot of wall. Now, I think, I'm not a practicing engineer, at least I don't design new buildings, but I think this is not what we will do in practice. I think we will use C walls in the core, or we will enlarge the ends of the walls. But Resist doesn't allow to do that. It's a pity. I think we will try to go around that using the CSOC software Gen Wall. And this is very powerful, and it's very easy to use, because you can define different bars in different locations, different sizes of the enlargements. You can do C walls. So I think we'll try to get around that problem using that software, but it's work in progress. Now with steel structures, same building size, different type of structures, and then the connections are giving us a lot of problems. All about steel is connections, right? So we are looking at moment-resisting frames, we are looking at braced frames and EBRs, and different type of floors. Now, I'm not sure if I can respond a lot to steel questions because I'm using Charles Clifton, and I just rely on him, and I don't have to worry about it. But my students are there, so maybe they can answer the questions. One problem we are having is the cost estimation. So this is from the QV Cost Builder app or web. And in theory, for this type of universal columns, different cities, we have different sizes. And connection is included. But this is a bit broad. And in fact, it's over-conservative. It's too expensive. It's not the same to make a simple connection with 4 bolts than make a very complex connection with several members in different angles. So it's more expensive, of course. So we are relying on the experts in here. We are using Steel Construction New Zealand. They have a connection guide, and we can do the costing much better, much more accurate. And finally, next year, I want to do foundations and earthworks. I will need to hire a geotech because I know close to nothing about geotech. And then facades, how we can design facades that are cheaper. Non-structural elements, what happens with both the displacement or drift-dependent elements like gypsum board, or with acceleration-dependent elements like hanging elements, and then do a detailed seismic performance to really understand what the buildings are doing, not just rely on preliminary design. Maybe do some low damage technology, some basic one like base isolators or dampers. And finally, I want to develop that tool that EQC wants to make available for everyone to be able to predict that cost accurately. That's all. Thank you. All right, I guess I am the master of ceremony as well. Yeah.
Take questions?
Yes.
I saw in the bus drivers list, there was no, sorry, Nick, there was nothing listed about dimension of grid, or whether we're looking at a long span or shorter span floor system, which I would have thought might be quite a driver. I know in some of the work that we've done around actually almost a similar program, but with a bit of a embodied carbon overlay, we've found that I think like you, that actually the increase in hazard factor doesn't lead to that much material increase on the system. The overall portion of increase in the overall structure is pretty small, but increasing the spans of things drives more material to span that distance, and then more material to embrace that heavier structure as well. So I was just interested as to whether that was one of the cost drivers that you were looking at.
No, you're right. It's not there. It should be some ratio, right, between the overall dimension, width of the building versus span or number of grids. But yeah, you are right. Having for a fixed width, less or more spans should have a difference. Yes. Thank you. Yep.
Were like the installation cost and time frame for each kind of system to be built considered? Because sometimes they pick, for example, precast because it's quicker, and time frame on how they do their sequencing?
No. It's built, the time frame is built into the cost, but not into the sequencing, into the organizing the construction processes. No, it's not. You are right. Sometimes it's difficult to it's difficult to capture that. Yeah. Yeah.
Just wondered if you'd considered the return on investment that a developer would be getting, rather than sort of presenting economical costs and more to build, that the language might be better, saying that it's increased, rather than reduced costs, increased return on investment. That was another factor.
Yeah, you are right, but I don't have control over the return. This is only the investment, right? I don't have control over 20 apartments at 1 million each or 25 apartments at 800 each. I don't think that's my objective. But yeah, that's the whole purpose.
Those comparisons between the different hazard factors, is that at a constant ductility? Because and have you looked at different ductility systems in those frames, for example, and what difference is that like?
Yeah, that's a very good point. For now, we are just looking at hazard factor as a proxy of everything else, basically. But you're right. You could design for a hazard factor of 0.4 with ductility 2, or a hazard factor of 0.4 with ductility 6. The problem is that is not easy. The preliminary design is not going to consider that. So that's why I want to have a structural engineering student to do a master, dedicate like 12, 18 months of his life or her life to solve that problem. Drift. I think drift is probably more important than ductility.
Is that to do with the non-structural elements or the drifts?
Damage is related to both drift and ductility. But if you have buildings that don't move, then you cannot have damage. But you are correct. There will be implications on non-structural elements because
The higher sort of, most of the damages will be non-structural on the facade.
exactly. So yeah, we will need to look at how exactly are the non-structural elements affected by changing the stiffness, because you are changing the stiffness of the building. Yeah. Yes.
I designed a 3-story hotel, sort of bit like overgrown 3604, and it was the bedroom wing and it had, like 7-metre long walls, the jib flower walls and things, and it ended up incredibly stiff because the length of those walls and the jib bracing formulae are all based on more like 1 or 2 metre long, 2.4 metre long panels typically, and then when you use the same formula to get a bracing element on a 7 metre long panel, it's incredibly stiff, and it's like 16 metres wide, so it's a very deep beam on the floor, and someone else actually analysed it, and basically got zero movement at the shear centre of the building because of the stiffness of the whole thing.
With timber flooring, timber
Yeah, well,
walls.
it's like bedrooms, sort of like 4 metres wide and 7 metres, 8 metres long, just an apartment, like a hotel room with a bathroom. And so in that direction, it had transverse direction, 7 metre long shear walls, 4 metre ceilings on both sides of the building.
So basically what you have is this. Walls, 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 walls.
Yeah. It was like using low technology because you've got a timber frame building, you need to fire rate it, so you use chipboard. So we use the chipboard for the shear walls as well as just using standard house technology.
Yeah.
And not having to put plywood and then more chipboard on it, so it's just using what was there and the inherent layout of a hotel block to get the...
I think we should do that. I think we should do that with, I don't have experience with timber, sorry. I know that it comes from trees and little more. But with concrete, we should do that. If we have 10, 8, 15 stories high buildings and we need to build walls, and if it's office, it's a little bit harder, but if it's residential, just use the structural walls to divide the building in apartments.
Actually, it was the question of putting a lift or double lift, and it was 2.1 metres wide lift frame, and it was 2 lifts wide, and those 2.1 metre long braced frames were actually less stiff than the 7 metre long timber ones, which is the opposite of what you think.
Yeah.
So you end up perceived stiffness, irregularity just wasn't there. Because of the amount of quantity of timber that you need to build it, and you've used it all, and you've used it all once, and low technology and all the rest of it, and lots of rooms.
I think that's one important point. I don't think we should design every building with base isolators and dampers. I don't think it's realistic.
Because then the only thing that was working on is P21 test rather than a plywood 3603 calculation. So those 7 metre long walls must have been, because basically they're not moving because they're so stiff. They're stiff as a steel lift frame, and so it was not actually. They'll actually be a lot better than what the test actually implies, because that's the only thing we've got to calibrate them.
Yeah.
So if you're doing they're looking at extending 3604 to more stories. So you know, if you've got lots of long walls, and Jip says, you know, brace the whole wall. And I needed to, using the bracing, the calculation of, you know, like 150 BU per metre, and then I had like 3.6 metres floor to floor on the bottom, and you know, services, and so it's high start, so that factored it down as well. And so I needed all the walls. The bracing at like 3604 says it should be done.
Yeah.
But in actual fact, there must have been a lot of extra strength there that's not even taken care of.
Yeah.
And certainly a little stiffness.
So, you know, there's maybe something I don't understand very well, but I think you explained it earlier that machine learning was going to be involved in the process. How was it incorporated in what the data you were showing, or was it yet to be?
So I am recruiting a professor from computer science to help me with that. My initial thought was to use an algorithm where you start introducing all the data and it spits out the results. But he had different ideas. I think it's not going to be machine learning at the end. It's going to be more of a, how do I say this? Like sort of a drop-down menu where you have concrete or steel, concrete, frames or walls, frames. So it's narrowing down the cost rather than in a huge cloud of data try to find your data point. But I can't worry about that now. I have to worry about that next year.
You have to use statistical analysis to work out all these figures? What?
You mean the cost value?
Working out, you know, 50 parameters and so many, how to allocate, or, you know, you've got the cost and you've got all 50 parameters, so you can do statistical analysis, say which ones are more important than others.
Yeah. That's cost driver analysis, yes. And not only which one is more important, but by how much. That's the key.
But that comes back to your big database, saying you've got a big database of buildings, so therefore it's covering the field. So.
Yeah, that's right.
Are you going to collaborate the results with real-life examples?
Yes. If you are working in a building where the client is happy to share the cost.
Yeah, that's what I'm saying. Like you're not coming back to the same issue that you started with.
Yeah. And I don't know how to solve that problem because it's not a technical problem. It's people don't want to share how much they paid for their buildings. Even to me, I mean, I'm not going to say who you are and what your building is, but yeah, I would love to.
Yeah.
Maybe what I have to do is go to an engineer and try to find some funds and go to an engineer, go to a quantity surveyor and design this building even though it's never going to be built. But still, it's not construction, it's estimation.
What about all the databases of like creating databases of historic buildings, of old buildings for seismic things, so that's getting a big database of, even it's obsolete, but essential technique, isn't it?
Yeah, but it's not as simple as saying, so the cost in Auckland per cubic meter of concrete now is $250. In 2005, it was $120. It's not as simple as that. Construction methods change, labor costs change, taxes.
But isn't that where things like, there used to be a handbook, Rawlinson's handbook?
Yeah, that figure,
QV.
yeah, it's QV. And that figure, the one with the division of costs, is from Rawlinson's. So yeah, I'm using the same that industry uses. We are just not going to build a building. Good.
I think we'll leave it there for this evening. I'd like to thank Enrique for coming in and presenting his research, which he presented last month, was it, at the CSOC conference?
Yeah, a month ago.
We're very lucky to have him tonight to share his information with us all. On behalf of the ASG, I'd like to present Enrique with a little token of our appreciation.
Good, thank you.
I'm sure you'll all thank Enrique in the usual way.